Okay, I'm going to look at a few of the very simple things that we do with looking at a single quantitative variable. And you can ignore this. So let's talk about descriptive statistics. 3 questions you have to answer about a quantitative variable: location, or maybe another way to describe this is to say the size. What are the sizes of the numbers that we're looking at? Variation, how scattered are they? And shape. Beyond location and variation, what should be said about the data? And I'm going to create some artificial data to explore these ideas. So I ran the command x equal r norm of 1,000. And when you run this, you won't see anything. Nevertheless, it does exist. And you can start asking questions about it. Like, what is the mean value of x? Well, it's 0.0247. What is the median? 0.019, very similar. The mean and the median are very close to each other. And the standard deviation is 1.04. That's kind of what I should expect, because the default values when I create random normal numbers is to draw from a normal distribution with a mean of 0 and a standard deviation of 1. I have to emphasize that this is normal. If you run the same set of commands, you will not see exactly the same numbers that I'm looking at here. You'll see something slightly different. That's because a random number generator does something different every time you use it, unless you take specific steps to control it. Now, why do you call something a measure of some attribute? Well, the reason is that it describes, if you do that change, if you do a change to every number in a collection of numbers, and you ask what would you want to have happen to the measure of location or size. For instance, let's suppose that I took my values of x, which I just created, and I added 100 to every number. What would you want to see happen to a measure of location of x plus 100? Well, think about it. After you thought about it, use the r command mean applied to both variables, then advance to the next slide and see. So please go ahead and do that. Don't be a complete observer, be a doer. If I look at the mean of x, it is 0.0247, blah, blah, blah. And if I look at the mean of x plus 100 is 100.0247, blah, blah, blah. You don't see the blah, blah, blah. So that's what happened. If you add 100 to every number in a set of numbers, the mean of the new set of numbers will be 100 plus the mean of the old set of numbers. The median, what happens there? What do you think is going to happen? Please do it. Then let's look. The median was, our original numbers was 0.019. And if I look at the median of x plus 100, it's 100. It just simply added 100 to the median. Variation. What do you think you should see in measures of variation or scatter or spread if you add 100 to both, to every number in a set of numbers? Well, I think it shouldn't change at all. They're just in a different place, but the way that they're scattered about is the same. They're just in a different place. And yes, that is exactly what happened. The standard deviation of x and the standard deviation of x plus 100, they're the same. There's no difference. The interquartile range, that is the distance between the 75th percentile and the 25th percentile, that is where you see the middle 50% of the data. You want to know the length of that interval, and that is a measure of variation. Let's take a look. The IQR, yes, the IQR is the same for both x and x plus 100. The range, the distance between the maximum value and the minimum value. Yes, it is exactly the same. So these things are good measures of variation. And here's a little exercise. What you should do is create a new variable x times 100 and see what happens to the values of the mean and the median and the standard deviation and the IQR and the range. What would you expect to have happen when you multiply the numbers by 100? That is an exercise for you. I'm not going to do it. Shape. The standard graphical display is the histogram. And also the box plot can be useful. And in base R, the command to do a histogram is just hist of the variable name. And there we go. And you see this looks like a normal distribution, if you know what a bell-shaped curve looks like. And here's the box plot. So I laid it out in the horizontal by including in the box plot command horizontal equal true as a second argument. And here's the summary, very useful. It gives the minimum, the maximum, the 25th percentile, the 75th percentile, the median, and the mean. Here's a different distribution. Here I used RUnif to create 1,000 random numbers uniformly distributed between 5 and 10. And there's the box plot. And there is the histogram. And you notice that there's no peaking at all in the histogram of uniform random numbers. Here's another distribution, a chi-square distribution with 10 degrees of freedom. Don't worry about what that is. But here's its histogram, and you can see that it's skewed to the right. If you have a hard time figuring out what skewed to the right or skewed to the left means, think of your foot and imagine that you got your shoes and socks off and you're looking at your foot. This looks like your right foot, doesn't it? Here's your big toe, here's your little toe sitting out here. That's the right foot. So it's right skewed. There's the box plot, and you can see the right skew even more clearly. Here's the summary. And that distribution was symmetric with a clear right skew, rather asymmetric with a clear right skew. Clear peak between 9 and 10. And the maximum value is an outlier. Let's use some real data. I've looked at the CDC data frame in a couple cases. So I'm going to load this data frame and then run str to identify some quantitative variables. And you can just click on CDC R data in the files pane to load it. So this is obviously run in Posit Cloud. And I can see that there's a couple quantitative variables that I could pay attention to here. There's height, weight desire, and age are all quantitative. These things say they're numeric, but they're really just no is 0, 1 is yes. These are really binary variables. Let's look at height. It's a quantitative variable and it's measured in inches. Because it is within the data frame CDC, you have to refer to it in our code as CDC $height. So here's a summary. It has a minimum value of 48 inches or 4 feet, a maximum value of 93, which is probably not quite true. I think that's false data. The mean and the median looks like 5 feet 7 inches. That appears to be normal. Here's a histogram. You can see that it looks kind of like a normal distribution. It's not too far different from normal. And you can see also here it looks very nice and symmetric. Age. Examine age. Describe what you see. I'll give you a few minutes to stop and look at age, CDC $age. So take about 5 minutes and pause the video and actually take a look at age yourself and see what you see. Then come back and restart the video. Okay, you're back. Let me take a look and see what I see. I do a summary and I see that the minimum was 18, and that's correct because that survey was only administered to people of 18 or above. Median of 43, a mean of 45, maximum of 99. Yep, people do live to be 99 or 100. There's the histogram, and it is definitely a case of right skewness. Looks like there's a peak around 40, which you could see up here. 43 and 45 those are the central locations. And it goes out to close to 100. If I do a box plot, I see the same thing. In the box plot, I can see more clearly that there's there's a certain amount of right skewness. Okay. So that's it. That's the real basics for looking at a single quantitative variable. Just using the tools in base R. We're going to look later and we'll get some better tools when we look at ggplot2.